How does your phone know the fastest route before you even start driving?
You type in a destination, wait half a second, and suddenly it gives you 3 routes. One is normal, one is slightly worse, and one takes you through 6 side streets, 1 suspicious left turn, and somehow saves you 4 minutes. So, what is happening here? Is the app checking every possible road combination? Is it guessing? Not exactly. The answer is graph theory, and once you understand the map, these navigation apps become way less mysterious. To us, a map looks like streets, buildings, highways, and neighborhoods, but to a route-finding algorithm, a map is not really a picture, it is a network. Every intersection becomes a dot. In math, we call that a node, and every road becomes a line. That line is called an edge. So the city turns into a graph of a collection of nodes and edges. That is the first big idea. The app is not thinking turn left at the coffee shop. It is thinking, how do I get from this node to that node using the cheapest sequence of edges? But not all roads are created equal. Some roads are short but slow, while there are other roads that are long but fast. So the algorithm gives each edge a number. That number is called a weight. The weight represents the time it takes to drive through that road. So this road might cost 3 minutes, this one might cost 8 minutes, and this one might only be 1 minute. Now the problem becomes much clearer. The fastest route is not always the shortest looking route. The fastest route is the route with the lowest total cost. So if one path takes 3 plus 5 plus 4 minutes, that is 12 minutes. And if another path takes 6 plus 2 plus 1 minutes, that is 9 minutes. Even if the second route looks longer, mathematically, it is a better route. Being the fastest is not the same as being the shortest. Being the fastest means having the lowest total cost. So at this point, you might think, oh, easy. Just check every possible road and find the fastest one. But there's one critical error with that. Let me explain.
You see, this would be possible if your cities had, let's say, 7 roads. But cities are much bigger. Each intersection has a bunch of options, and each one of those options has another bunch of options. This continues to grow exponentially, and by the time your phone is done calculating all those options, you could have arrived to your destination even if you took the longest possible road. So, the algorithm needs to be smarter.
One of the classic ways to solve this is called a Dijkstra's algorithm. The idea is beautifully organized. Imagine every intersection has a sticky note on it. At the beginning, the start node gets a sticky note that says 0 minutes, because it takes 0 minutes to get to where you already are. Every other node gets infinity, which basically means I have no idea how to get here yet. Now, the algorithm looks at the start node and checks its neighbors. If this road takes 4 minutes, then its neighbor can be reached in 4 minutes. So, we update its sticky note. On the other hand, if this road takes 7 minutes, this other neighbor gets 7. Now, the algorithm asks one question. Which unvisited node has the smallest number? That node is the cheapest place we know how to reach so far, so we lock it in. Once a node is locked in, Dijkstra is saying we have found the fastest possible way to get here. Then, from that node, we check its neighbors. Maybe getting to this node costs 4 and this one 3, so the total cost becomes 7. If that is better than the number currently written on the neighbor sticky note, we replace it. If not, we simply ignore it. That is the entire process. Pick the cheapest node, lock it in, update its neighbors, and then repeat that all again. You can look at the graph for a more visual explanation of what Dijkstra's algorithm does, but overall, you can just think of it as the most responsible person in a group project. It never panics, never guesses, it just calmly updates the sticky notes until the destination is finally reached. Another way that you can imagine Dijkstra's algorithm is flooding the city with time. Imagine you pour water at the starting point, but the water does not spread based on physical distance. It spreads based on time. Fast roads let the waves move quickly, while slow roads delay the wave. The first places the waves reach are the fastest places to get to, and then, when the wave finally reaches its destination, the path it took is the fastest route. That right there is why the algorithm does not need to check every route. It explores the map in order that matters the most. Cheapest first. And now, once the final destination is reached, the algorithm can trace the route backwards. Each node remembers where it came from, so the destination points to the previous node, and the one before it, and the one before it. And eventually, we're able to trace the path all the way back to the start. The highlighted path is the answer. Not because the app had a feeling, not because it guessed, but because the graph kept track of the cheapest known way to reach every important point. The final route is just a chain of choices with the lowest total cost.
Now, Dijkstra's algorithm is very strong, but it has one big flaw. It is extremely thorough, and sometimes even too thorough.
Let's say a destination is east. Dijkstra might spend time exploring roads to the west, north, and south because it only cares about the cheapest distance from the start. It doesn't really have a sense of direction. That is when another algorithm becomes useful, A-star. A-star is like Dijkstra with a sense of where it is trying to go. Instead of asking, how much has this route cost so far, A-star also asks, how far do I probably still have to go? So it uses this idea, cost so far plus estimated cost remaining. In symbols, that looks like f of n equals g of n plus h of n, where g of n is the cost so far and h of n is the estimated cost. You can think of Dijkstra exploring like a flood, and A-star more like exploring like a flashlight. It still uses math, it still uses cost, but it points the search in a smarter direction. In short, A-star is a combination of Dijkstra and direction. And this is where the real navigation gets interesting. Traffic does not necessarily change the shape of the graph. The roads are still there, the intersections are still there, but traffic changes the weights. A road that used to cost 4 minutes might suddenly cost 18, and when the weight changes, the best route will change too. That is why your navigation app sometimes says rerouting, which emotionally feels like betrayal, but mathematically it makes sense. The graph has changed, not the dots, not the lines, the numbers. And once the numbers change, the cheapest path may be completely different from what was initially the cheapest path. So, to sum it up, when an app finds the fastest route, it is not looking at the map the way we do. To us, it looks like streets and turns. To the algorithm, it looks like dots and lines. Intersections become nodes, roads become edges, travel time becomes weight, and the fastest route becomes the path with the lowest total cost, not just the lowest total distance.
That is graph theory, and that is optimization. Ladies and gentlemen, that is the applied math behind navigation app. Hope you guys enjoyed this video and make sure to like and subscribe. Thank you.